Looks good. Okay. Yeah. Guys, just if you have any doubts, put the stuff in the chat or open your mic and speak up. Yeah. Thank you, guys. Bye.
Okay, is the screen visible?
Yes.
Screen visible. Okay. Okay, start பண்ணலாம். So talking about introduction. So you can see the image there, right? You can see two people have been spotted there. But if you see in real eyes, you could not see those people there. And if you closely observe the image, you could see the two bodies. I mean, consider the human as objects. The guns are also there, right? So those are also objects. These objects are visible in some type of camera, which is IR camera. Okay. uh, you could see there's some kind of glow or called a radiation emitted from objects captured by the camera. So why are these radiation emitted and how can it be emitted? So we have something called as an absolute zero temperature, in which the temperature is absolutely zero, as you know. If some object possesses a temperature which is more than the absolute zero temperature, it would basically emit a radiation. So this radiation basically falls under IR range. Okay, va? So that's why we use an IR camera to capture these night sense vision cameras. Okay, va? So this is what this image basically sets up an foundation for the quantum physics. So this is all learning objective. We'll skip. Okay. If you consider physics, there are three main pillars. Classical mechanics, which is basically called the Newton domain. Next is electromagnetism, which talks about this radiation, matters, how electricity and magnetism both combine to give rise to the EM waves. So these all concepts come under this electromagnetism. Third one is thermodynamics. Thermodynamics, basically, as the name suggests, talks about the interaction between the matter and the radiations. So this is what these slides impact. Next, the question, what is light? So a light is basically an electromagnetic wave, where the electricity and the magnetism, both the waves, are perpendicular to each other. Okay, wow. So these are some of the formulas of Maxwell equation. You can just see through it and come. So moving on to this. So as the definition says, light is an EM wave. This is more important. It's an EM wave which can propagate through the mediums. The mediums are mentioned there. So a visible light, I mean, you could see the light in your eyes, the range of colors, all this called as a visible light. So the visible light has a wavelength uh, lesser than, you could see the range there, right? It lies between the infrared and ultraviolet. Infrared has a higher wavelength. Ultraviolet, UV, which is asing, and have a lower wavelength. So visible light lies between these two. So to define light, we should have some characteristics, right? I mean, if this is a light, we should have some characteristics there. So you will have 7 characteristics of light. This is considered more important because they might ask what are the characteristics of light. First, a light should be an EM wave, electromagnetic wave, simple. Then as it is in wave, it should have some characteristics, right? So the characteristics are wavelength, frequency, amplitude, and it should lie within a spectrum. Okay, and these all 4 parameters should be well defined for that wave. Some waves are there where the frequency or spectrum might not be well defined. We can't call those waves as light. Okay, these 4 parameters should be well defined for it. Then it should follow the diffraction. What is diffraction? Bending around of a light around the corners or edges. Okay. As you can see in the Young's double slit experiment, all those, the light will bend, right? So it should show the property of diffraction. Next is interference. Interference basically operates on a principle of superposition, where two different waves can compose and form a higher trough, which is constructive, and both can cancel out and form destructive. Okay, so it should basically form a constructive destructive type of formation to follow the superposition principle. Next is polarization. So polarization, you could, I mean, there can be different types of wave, different in different planes. You should be able to make it into a single plane wave. So that is called as polarization. So as light is a transverse wave, we can restrict all the waves to a single plane. So we can restrict, I mean, restricting to a single plane means the oscillations can be controlled to pass through a single plane. Okay. Next is energy and momentum. So if a wave is there, it should have a defined energy and momentum for itself. So the formula states here, you can see I energy and momentum, those two formulas there, which is simple. Seventh one is the continuous absorption and emission. So a light should have an energy which should be in the form of a continuous absorption or an emission pattern. Okay, so these are the 7 characteristics of a light. So if these 7 satisfy for a wave, we can basically call it to a light. Okay, any doubts? Okay, I will proceed to next. This is just an introduction. This all states about like physics has discovered all. There's no new nothing. Lord Kelvin would say at the time, but eventually after that, the quantum physics will evolve and come out. So coming on to, we have all studied about the classical physics, right? Then why do we need something as in quantum physics? So, I mean, defining everything in classical physics, later on, they discovered 2 major problems. What are those problems? One is a relativistic domain. Okay. So basically Einstein showed this problem. When things move near the speed of light, the Newtonian mechanics break. Okay, we have some set of rules called Newtonian mechanics. So when any object forced to go near the speed of light, it would break this law. So that is the first domain. Second is the microscopic domain. So people using classical physics were not able to define how the atoms interacted with light. So this was the failure in the microscopic domain. The third one, which is the major among the reasons for the development of quantum physics, was the classical physics is not able to explain the black body radiation. So don't worry, black body radiation, we'll cover it in the next lecture. This is all I explained in the previous thing itself, IVA sensor all. So coming on to black body radiation. So what is a black body radiation? Basically, there's a black body. It is, I mean, as the name suggests, it should not be eventually in the black color. It's just got a name called black body. So when a body can be anything, a surface or an object can anything. When it is able to absorb all the electromagnetic radiation falls on it, it is called a black body. So this black body will be a perfect absorber and a perfect emitter. What does it mean? Every radiation falls on the black body, it would be able to perfectly absorb it without even leaving any single pieces, crumbs left. And it will be able to emit everything it has. So that means perfect absorber and a perfect emitter. Any light comes, it absorbs, fine. But the black body will emit some of the radiation, right? Every radiation, right? That emitted radiation is called as a black body radiation. Yeah, next. We are seeing some of the characteristics of the black body here. One is here, you could see the absorptive power. What that they say is, basically it's a ratio of the heat absorbed by heat incident. As you can see, power means output by input, right? So output is the heat absorbed by the body and input is the heat instant on the body. So this ratio would always be between something as a probability. I mean 0 to 1. It would always lie between 0 to 1. So if you see, black body definition is what? It is able to emit all the radiation it absorbed, right? So in that case, the heat incident on the body will be equal to the heat absorbed by the body, correct? So as both the terms are equal, this ratio would lead to one value. So we could say a perfect black body's absorptive power is 1, which is actually somewhat hypothetical, but this is the definition. So you can also define the black body as absorptive power equal to 1. Okay, and it should absorb all the radiation falling on it, irrespective of the angle, frequency, and wavelength. Okay. So then coming on to a single point, I mean a clarification point, you could see the bodies, objects are glowing. But why we are not able to observe every radiation of every bodies around us through human eyes? So the thing is, so us humans and some things are relatively cold compared to huge temperatures. So our atoms inside us will vibrate very slowly, which would eventually lead to a wavelength of radiation, which is long. The wavelength of the radiation would be long if the vibration is slow. So this wavelength will usually fall in the IR regions. So that way, most of the radiation which I emit or you emit is not usually seen by the human eyes. Rather, we can cover it using the IR cameras. Okay. So yeah. Next, black bodies and hypothetical concept as now. How could we demonstrate it practically? So we use something called as Ferris black body. That is not in a concept, but remember the name Ferris black body. So what you will do, you will take a spear and you will have a cavity, right? You will polish it and make it completely black inside. And you will let only a narrow orifice for a light or the radiation to pass through, as you can see here. So the definition is given here. And you should see that the black body has a zero reflection and zero transmittance. Why? Because everything falls on the black body will be emitted because it's a perfect emitter, right? So if a radiation falls on a black body and if it reflects, it means that it is not 100% absorbent. So a black body cannot have a reflection type. So it shows a zero reflection. Zero transmittance. If some radiation passes through the black body, then the black body will not contain that radiation. Correct? So it should not let any of the radiation to pass through it. So basically, it cannot be transmittive material. So a black body will be a zero transmittance. So this is what these 2 points here state. Next, this graph. Observe this graph. So the x-axis is the time and the y-axis is the temperature. There are the x and y both bodies. Consider x and y to be both bodies. You could see that the steep of the x is more than the steep of the y. What does it say in the graph? Interpret. When there's a specific time, the x loses more temperature because temperature is on y-axis. So loses more temperature than y does. Correct? So here we should note an important term which is known as emissive power, which is represented by capital E. Okay, so what is emissive power? As the name suggests, the amount, the power, okay, the power of object to emit, or you could simply say how fast or how powerful could an object emit the radiations out of it. So see the graph, you could obviously see X loses a lot of temperature than Y in a particular amount of time. So X has a more emissive power. It emits more than Y. So you could say the emissive power of X is greater than of Y. Correct? So now here comes, but in the options, they have given only observed power. So remember, there's a Kirchhoff law which states a good emitter must be always a good observer. Why? Because the emissive power divided by the observed power is always a constant for any body. So if there is if a body is a good emitter, to make it a constant value, it should be a good observer also. Are you able to get it? So a good emitter will be a good observer also. So here, what is the good emitter? It's obviously X from the graph. So you could say it would also have a greater absorptive power. So option A here would be the right option. So that is what the below statement state. Next, observe this graph carefully, which has a spectral energy density and a frequency graph. So spectral energy density is basically the energy per unit time per unit area. Okay, wow. So the first observation from this you could make is here there is, you could see this this forms a smooth curve, and you could see this curve does not depend on any of the composition of the material. There is no axis called the composition of the material. So the radiation for an object only depends on the temperature, as we saw before, and does not depend on the composition of the material. So that is what the first observation we make here. Observation, sorry. Second observation. Look at the graph more clear. I mean, here at the point, we have reached a max value. After this max value, the graph starts to go down. So the second observation is what? There is some point at which there's a point which is called the Vmax, the maximum frequency, at which the energy density is high. And after that Vmax, this graph continuously falls down. I mean, the spectral energy goes down after that particular frequency. Third observation gives rise to the Stephen Boltzmann's law. So it simply states that if you take the integration of this curve, you could find the area under the graph, right? So what is the area under this graph? What is spectral energy density? As I said, energy by time by area. So what is energy by time, which is power? What is power by area? Power by area is basically the total intensity, right? So the area under the graph gives you the total intensity at a particular temperature. Next, and this whole graph is for a single temperature. Okay, remember that. So what does Stephen Boltzmann's law states? The intensity is basically proportional to the temperature raised to the power 4. So obviously, if there is an sign to make it an equal sign, we introduce a constant. The sigma is the constant here. The value is 5.67 into 10 power minus 8. Okay, these and all are defined. You can see it is defined here. So you could say the intensity depends on the temperature by the power of 4. This is for a black body. For a regular body, we introduce a term of emissivity. Okay, what is this emissivity? As I told, the emission, the how much emission it can give. Okay, why for the black body the emissivity term is not there? It is there, but the emissivity of a black body, as said, is 1. Okay, so the emissivity term there disappears. As this is 1, we just simply write it sigma T power 4. Okay. Next is this question. You could use the formula P is equal to sigma A power T4, and everything is given. The P is given, the A is given, and the sigma value is also given. You can just substitute and take the fourth root of the value. You would eventually end up on the T. Okay. So next, these graphs. You could see this graph is plotted for different temperatures. What you can observe here, you can see the temperature third temperature is more higher than the temperature 1. So this temperature is high, this temperature is medium, this is the lowest temperature among the 3. So you can observe when temperature increases, the maximum, the peak of the curve shift towards higher frequency. Frequency is going this way. So when there's a temperature increase, the peak of the curve shift towards higher frequency. So what you can say from this, the frequency is proportional to the temperature. Okay, so you could also say if what is frequency and the wavelength relation? Frequency is basically inversely proportional to the wavelength. Okay, so here frequency is proportional to temperature, and frequency is inversely proportional to wavelength. So from these two, what you can say, the wavelength will be inversely proportional to the temperature of the object. Correct? So here there's a sign. So make it, you should make it into equality. So you introduce a constant called as the Wien's constant. The value is given here. Okay. So from this, what you can say, the maximum wavelength emitted will be the constant divided by the temperature. So this is what is Wien's displacement law. So this is the formula here, the constant value you remember. Okay. So coming to the question down here. So you can say, as I said, the wavelength is inversely proportional to temperature. So which has the more wavelength, which is lambda 3. So it will have the lowest temperature. Okay. Which has the shortest wavelength, which is lambda 1. So it will have the highest temperature corresponding to is T1. So option A, which is T1, T2, T3. The temperature one is more is the correct here. So this is a simple question. So next, talking about this. So here you consider this is a theoretical approach. Okay. So the radiation is basically considered to be a thing which is arising out of atoms. So here consider atom to be some kind of oscillator which oscillates continuously there. Okay, and this oscillates in a harmonic method. So that is what referred in the second point. So as you know, if the energy is higher, the oscillation speed would be obviously higher. And if the oscillation is higher, the distance it covered will be higher. So which essentially means it will go more displacement from its mean position. So this is the thing which is talked here. Next, coming on to this graph, observe this graph. Okay. Before that, we go on to a formula, which is Rayleigh's energy density distribution. So how do we get this formula? So total energy density, which is this U, right? Total energy density is basically equal to the number of oscillators, which is basically the oscillator. Like I talk about atoms, the number of which oscillates on its mean position. So the number of oscillators per unit volume into the average energy of one oscillator. So basica, what they say here is, ஒரு இடத்தோட energy density if you have to find, we should multiply the energy of one oscillator into the total number of oscillators present in that particular area. Okay, which is very basic. So here the term KT is the average energy, and this term talks about the number of oscillators per unit volume. Yeah, looks fine, pretty good. But if you plot a graph for this formula, you could see it follows this red line. But before we saw the graph goes into a smooth curve. Then what might be the wrong error here is what is talked in this slide. So if you convert this formula, this is in terms of frequency. If you convert it terms into a wavelength, you could see the formula comes to this. And if you observe, the denominator term is lambda raised to the power 4. So take a situation when wavelength reaches to 0, nearly 0. What happens? As it is inversely proportional to wavelength to the power 4, this energy exponentially increases, which leads to an infinite energy. Can infinite energy be a real case? No, because we have something called as energy conservation, right? If you give a system an energy, that energy should be conserved. So if there is an atom, obviously that atom is not going to have an infinite energy. So when the atom reaches to a wavelength of 0, it cannot also emit an infinite energy, right? So this is the anomaly formed by the Rayleigh's energy distribution. So we could say, as you can see the graph below, this fits for higher wavelengths, but not for lower wavelengths. Okay, so Rayleigh's energy distribution fails at lower wavelengths, but fits very well at the higher wavelengths. So next we come on to the Wien's energy distribution. This is opposite to Rayleigh's. This fits very well for the lower wavelengths, but performs badly for the higher wavelengths. Okay, so here you can see the formula, which is derived using the Boltzmann law and the thermodynamics laws. Okay, there's no need for the derivation here. C1 and C2 are constants. So this is inversely proportional to lambda power 5. And this formula is represented here in the terms of frequency. Simple. Next is a concept called as ultraviolet catastrophe. So what does it say? As you saw in the formula here, when the wavelength decreases to a level where it approaches 0, the energy shoots up to infinite. So this is not a realistic case, and which is also an observed concept, right? As I said, it cannot have an infinite amount when we set to a particular amount of energy. So this condition is said to be the UV catastrophe. Okay. Next, if you see this formula, we obviously know this is not matching what our ideal graph looks like. So what might be the error in this? 8 pi is a constant, so it might not be the error. Wavelength, no, wavelength is obviously in the denominator and there's no error because wavelength is a measurement, right? So the only spot for the error is this average energy. It's not about the average energy, but the way we consider to calculate that average energy. So that is the failure of this. Okay. I'm stressing on this point. It's not failure of the average energy itself, the derivation itself, but the way we consider the system for an average energy. Here, all this talked about, all this derivation KT, we used an continuous energy system. All the radiation exchanges energy is considered to be continuous. So that's why we end up on KT. So that is the error. If we consider continuous energy, we end up in an error formula where it is not satisfying the whole curve there. Okay. So we'll finish it off there. So here comes this formula. So using the Wien's displacement law, you could say that the temperature is inversely proportional to wavelength. So this simply becomes equal to the wavelength of North Star divided by the wavelength of the sun. So you can just calculate, just substitute the values, you can calculate. These all for these 4 questions, all the answer is the frequency, wavelength, and the temperature relation. Okay, well, do you want me to explain these questions or shall I move forward? Anyone wants these questions to be? Okay. First question, why do different atoms glow with different colors? So as I said, every atom will have its unique structure and it will have its unique energy levels and unique radiation amount, because every object will have these emissive power, absorptive power, everything different. So obviously radiation will also differ. So if radiation differs, obviously the wavelength also will differ. So the wavelength will, in the visible region, the wavelength will give rise to different colors if there are different wavelengths. So that is why we could see the atoms glow with different colors. Okay, wow. Second question. Coals of a campfire or coils glow red. Okay, this is similar because it is at a particular temperature. Obviously, the temperature will give rise to the radiation. But why red? In the color scale, you see red has the highest wavelength or lowest wavelength. Anybody answer?
Highest.
Highest. Okay. Highest than egg. Yeah. Okay. So the campfire or coils are it is obviously having a good amount of temperature, but not a greater amount of temperature to exhibit higher level of colors like blue or something. So it exhibits a good amount of heat, but not highest amount of heat. So that's why it falls under the wavelength region of red. So it glows in red. Next is, why do even hotter they're talking about the coals and the heat above these coals and campfires, why those objects glow white? See, so blacksmiths, they're talking about blacksmiths. So more hotter object, obviously every area will not be uniformly same containing the same heat, right? There might be difference in heat if you consider an object. So difference in heat give rises to different wavelengths, wavelength radiations. So more hotter object, which is not uniformly heat, obviously will give rise to different wavelengths colors. So as you can see, when many wavelengths colors combine, they form a visible white light. Correct? So that is what give rise to this. Next, we are getting onto more hotter objects. Why do they glow blue? So as you can see, blue blue lies on the first part of the visible color. So when the temperature is getting to an higher extent, if you take the relation, T is inversely proportional to wavelength. So you'll get into a lesser wavelength. So lesser wavelength corresponds to which color? Blue. So that's why the objects which are very, very hot fall in the spectrum of blue. So these are the 4 questions, and this is not needed for the ensign. So you can just skip these states. You just learn these n formulas, which would obviously be derived later. Okay, so you don't have to worry about this. Next, next, as we explained, this is what going on here. Note, Planck made a proposition. You know that this formula didn't fit for all the wavelengths, right? So Planck made a proposition there. What he made was, if the energy, the total energy is basically the total energy what we talked about is kT, correct? So he proposed when the frequency approaches 0, this energy would be kT. And if frequency approaches infinity or larger values, this energy should reach to 0. Then only we can get this perfect curve. Okay, well, this curve state this. So this is called Planck's proposition of this curve. So as you can see, if you consider the energy to be a continuous wave stream, the energy comes to be kT, which is obviously wrong in many cases. This gives this curve and not an uniform curve as we derived. So what Planck said, consider the energy levels not to be continuous like this. You can see it is continuous. The atoms can exist anywhere in the point. Okay, so he told, no, this is not how it exists. there is a defined energy shells in which the atom should be placed on the top of the shells. And these are energy levels, okay? And these atoms can only exist on the energy shells and not any in between of the energy cells transisting, roaming here and there. It should only exist on the top of the shells and not in between the shells. Okay, and these every shells will have a defined energy level. If we consider this case to be the energy distribution of an object, then we would be ending up in a correct formula which give rises to the ideal graph we stated. Okay, va? So here talking about quanta. What is quanta? Quanta abdina, it is a discrete packet of energy. Okay, va? You might confuse with what is quanta and quantum. Okay, va? Quanta is basically a single energy packet. Okay, whereas a quantum is a collection of energy packets. Okay, this is basically okay. Wait, I might be wrong. So coming back again, quantum, sorry for it, quantum is a single energy packet. Okay, quanta is a collection of quantums. Okay, I'm making it clearer. Collection of quantum is quanta. Okay, these are the two difference between the terms quantum and quanta. Okay, to make it clear. So as you can see, these are in between these energy shelf. As Planck state, it should not exist. So everything settled down to the shelves, as you can see. So this is a perfect energy structure, as you can see. Okay, yeah. This graph basically state, like you can see the states, right? These states, you could see the gap there. Correct? These gaps, right? Obviously, as I said, every state has an energy, and these have an energy difference. The in-between gap states an energy difference. You could see at the less frequency side, these are very strict, and at the high frequency side, these have a lot of gap in between them. So what does this say? When the frequency is small, the energy gap between the shells is very small. Okay. So what you can conclude here, you need less amount of energy to kick any of the electron from one shell to another shell, which is basically can be done as it is in less energy, which can be basically done in the normal room condition itself. Correct? So an object with a lesser frequency can an electron in that object can actually make it to the next shelf even in the room temperature. But the frequency, when the frequency increases, and quanta here should possess a lot of energy to go up to the next level. So we need to heat in this case. Okay, so this is the relation between the frequency and the energy level difference here. Though this is what the whole graph explains. Next, this postulate I said, now everything has a defined level of energy. Okay, so what Planck states, the first postulate states that the energy is proportional to the frequency. As you can see, the lower energy has a lower energy, sorry, lower frequency has a lower energy, and a higher frequency had a higher energy. So this is what the first postulate. Next postulate, the second postulate is you would add an n term in front of this. What is this n term? This is an integral value. It can have any values like 1, 2, 3, 4. What does it state? That the atoms cannot exist in the transitional states. It can exist only on the safe states, the stable energy levels. So this is HV, this is 1 HV, 2 HV, 3 HV. So this 1, 2, 3 is the N, which is an integral value. Okay, so this is what the whole thing states. Next, about the fourth one. Yeah, this is the thing I explained before. The atoms will be a tiny oscillator, it will oscillate, it will create energy. All these blah blah stuffs are given here. The radiation comes out. Okay, next, Planck's approach we talked about, right? How did he approach? How he made things? Yeah, that is what the both revision slides talks about. Then we come to the famous derivation, calculation of the average energy or an oscillator. Okay, so see the states. Every state we denote by n0. Next state is n1, n2. We'll have till ni states. Okay, so here is a defined formula. What is defined formula? So this n represents the number of oscillators in each level. So n naught represent number of oscillators in the ground level. Ni represent the number of oscillators in the ith level. Okay, well, that is what Ni depicts here. So, according to Boltzmann's statistics, you can say the number of oscillators at ith level is equal to the number of oscillators at the base level into e to the power some term. So this term you know. Okay. So this is the whole formula. So n naught la how many oscillators I will have? N0. Up n1 la how many oscillators I will have? N naught into e raised to the power energy level of 1 divided by kT. Correct? So you can go up to Ni. சரியா? So இப்போ இந்த சிஸ்டமோட whole number of oscillators நான் எடுக்கணும் அப்படின்னா, I mean, if I have to get the whole number of oscillators in this system, I should add every number of oscillators in each level. Correct? So what I will do, I will add n0, n1, n2, n3 till ni. So here they expanded the n1, here they expanded the n2 using this formula. Okay, va? So they expanded this. Okay, so you will get this equation. Now you can't derive anything from this equation. So make an assumption x is equal to e power raised to the term. Okay, va? Now what you can do, every term has an n naught common. So you take the n naught outside. If you take the n naught outside, the remaining terms would be 1 plus e power the term, e power 2 into the term, e power minus 3 into the term, and it continues. Okay, va? So you consider this term to be x. So this whole thing becomes what? 1 plus x square plus x cube and follows. And leave n naught. This inside equation, basic mathematical formula, leads to something which is equal to 1 by 1 minus x. Correct? This whole term. So they have substituted here and they come to a beautiful equation n naught divided by 1 minus x. So the total number of oscillators in a object is what? This. Keep it. Don't substitute the x value. Okay, well, keep it the same. Next, we have to get the total energy density. Correct? Total energy of the system we should get. I'll explain why we calculate all these to get the average energy. Okay, well, next I get the energy density. So as you'd see, you calculate energy for each level, add those, you will get the total energy of the system. Okay, well, so what is energy? It is basically epsilon into the thing there. Okay, well, so it is basically, as mentioned, the product of number of density of oscillators in each energy level and the energy of each oscillator. So every energy level will have a particular energy, right? The first level will have h mu, the next will have 2h mu. It will differ, right? So the number of oscillators in that particular level into the energy level of the respective level. So if you form that, you'll get a beautiful equation. Again, you will end up this term. So make it as x. Then you will get this formula inside. So what does this say in mathematics? 1 by 1 minus x the whole square. Okay, well, so you get this equation for total energy density of a system. Okay, so you have beautifully considered what total energy you found, total number of oscillators you found. So to calculate the average energy, you should divide the total energy and the number of oscillators. Obviously, to find an energy of average energy of a system, you should take a total energy and the number of participants in there. The participant is the oscillators, correct? So what you do, you basically divide these two. Leave it here. Okay, what they have done here is basically split this. You could see this term. Okay, they have substituted and they have formed this equation. But no need to make this all complexity. You just keep this equation as itself. Okay, so what you do, you take this total energy divided by this equation. Then you would be able to form a beautiful equation of what is given here. So what we have arrived, average energy. This average energy where you saw, there you saw something called as KT, right? That is the average energy, correct? But here we get an average energy of this formula. Beautiful. So this is the calculation of average energy. Any doubts in the derivation? Okay, I'll move forward. Next, first, what we calculated the average energy, but there's a term before it. Okay, well, and the energy we had a term before it. What was it? The energy density. Energy density into the average energy was the whole term given there, right, by Rayleigh or Wiens, right? So as you see, this is, I mean, the derivation of this is not necessary for you. So you just remember this is the energy density term there. Okay, so you multiply the energy density, which is this term, and the average energy, which we calculated in the previous derivation. So the energy density radiation between V and the next level, which is V plus dV, is this in whole, and this is called as Planck's distribution. Okay, you end up at this formula. So this will fetch you, if they ask, this will fetch you around 10 to 15 marks if they ask anything. Okay. This derivation of this state is not necessary. Okay, that is pure max. You take spheres, you take things and do. So not necessary. So the same slide is repeated. Hippo, we see different cases using this formula. Okay, well, this formula is settled. What we are going to do, we are going to say that this formula accounts for Wiens as well as Raylines. How do we say that? First, take a shorter wavelength. Shorter wavelength எடுத்துக்கிறோமா? So take this exponential term. Okay, va? If there's a shorter wavelength, it means there's a higher frequency. So higher frequency, the exponential term, it is in the numerator. So this whole will become a large value, which is obviously greater than 1. So in this case, what we will do, we will neglect this -1 here. Because if there's a larger value, neglecting a minus from that large value, it's obviously it is going to remain the same value, right? It's a mathematical approximation. So you're going to remove this -1. You're going to end up in this form.